Yeah, well, thank you very much for the introduction. I've never been introduced as a rock star, but there's always a first time. So again, and thanks very much for the invitation here. I do appreciate it. What I'm talking about is something I've been working on for a very long time, connections between computer science and the brain. So progress is very, very slow in this direction. So people ask me, why do I do it? Well, I suppose from the computer science side, the argument simply is that we know so little about the brain, and we believe it's some computational object. So if computer science can't help us, then computer science is no good. So it's really a challenge for computer science to contribute something to neuroscience. So what I'm going to talk about, so maybe it's best to start what I'm not going to talk about. Okay. You will be relieved. But a bit more seriously, so I did work in machine learning, and my interest in neuroscience started with the idea that maybe, because of my knowledge of machine learning, and learning is important, which it is, maybe I can, I've got some special angle on the brain. But then I discovered that that's not true, because there are basic unsolved problems about the brain which are much, much, much simpler. Okay, so nothing as complicated as generalization, induction, stuff like that. So even things like, so if you meet a new person, you have some memory of the new person, what does your brain actually do? How many neurons do we devote to this memory? Is it 1, 10, 10 million? And maybe 1, maybe no one believes it's 1. But otherwise, no one really knows. It could be any number like that. Of course, another question is whether this question is well posed. Do we really assign memories to a fixed number of neurons? But so we'll discuss this. So of course, what I'm really interested in is some mechanistic explanation of how the brain does simple tasks of memory and learning in a way which satisfies a computer scientist, that there are states and algorithms and actions and transitions and some very concrete, I want a very concrete description of how the brain works. So maybe in 50 years' time, a neuroscience course will not be so different from a, let's say, algorithms course, where you study actually the processes in the brain. So that's what I'm interested in. So I'm really interested in how the brain works, not in technology, not in anything else. And the general methodology, which I'll say several times, is that I want to find some feature of the brain which is impressive, something which is hard to explain, something which is quantitatively hard to explain, and I want to explain it in some model which maybe says something. Okay, so I am really interested in symbolic processing, not training networks to recognize elephants. Okay, and what's symbolic processing? Well, what impresses me is that we can have a discussion at a symbolic level. So you know what green means and what fox means. And I'll tell you that there's a restaurant called the Green Fox. You can handle this information, not too hard. And then I tell you that I went there, it was a bad choice. Okay, you can start a different mood, you can handle that too. And it was recommended by Joe. I was there when I heard the election results. These are all facts. You can just build up this complex data structure in your mind, which relates to some previous knowledge. I can even tell you some of this is not true. You can handle that. So the question is, how do we do this? And what's impressive isn't that we can do this on a small scale. What's impressive is that we can do this through a lifetime, hundreds of thousands of such actions on top of each other, which do not compromise your earlier memories, not too much. Okay, so of course psychologists have studied these phenomena, and just the one notion I will use is chunking. So the well-known idea in psychology that these concepts aren't all at one level in our minds. So if I tell you that the Green Fox is a restaurant, they can deal with this information. It becomes as a basic notion, as primitive as a green or fox, it's a restaurant. If you learn mathematics, you pile definitions on top of each other very deep, but when you're an expert, even the most complex things become as simple for you to process as a basic level one. So that's chunking. Okay, so that's what I want to explain. And so cortex can do this for hundreds of thousands of tasks in succession without compromising the early ones too much. Of course, it may. So clearly we have a capacity, finite capacity. So what's that? And basically, if you ask, what does the brain actually do when you do this? What changes happen at each input? So there's no agreement. And what I would like to point out is that, so in some fields of science, there are three main theories, and someone has to do an experiment to decide which one was true. Okay, but there are other questions in science where there are no theories. Okay, where no one can have an explanation which even plausibly explains the facts. And I think these questions for the brain are more of the latter category. That it's not that there are theories around. People don't. You go to a neuroscience department, people don't put up their hands and tell you, this is how I think it's done. It's kind of, you get some sort of silence. Okay, so this is what we're trying to explore. Okay, so I'll build a computational model. So I'll just have to list a bit more particularly what I care about in these phenomena. Okay, so one thing I care about is that you do have one-shot learning. If I told you about this Green Fox restaurant, I told you once. I don't have to rehearse it 1,000 times to keep your memory going. Okay, so it's quantitative. There's a large number of tasks you can do over a lifetime. So what this number is isn't so clear. So there's some study of this, expert knowledge in chess openings or things like that. Okay, it's not quite clear what the number should be. It's probably could be higher. So the third point is that you're not just recording facts, but you're also making the brain ready to do something, to use the facts. Okay, so I view these things as I'll make it clear later on as a sub-circuit creation. So the point is, if you learn some association, you learn that Green Fox is a restaurant, and then you know something about restaurants, you can chain these associations in your brain very fast. It's not that you have to examine each statement, re-examine it later on. So this is constrained by the fact that our brain, in facts which we know very well, we're very efficient at acting on them. Okay, so and these subcircuits can be composed on the fly when evaluated. So you learn all these things for your lifetime, and you can really quickly use them. So this will be quantitative. So your brain isn't infinitely large. We've got a fixed number of neurons, and the main parameters are neuron numbers, the connection numbers, how many neurons each one is connected to, and connection strengths. So synaptic strengths. So that's very important. Okay, let's go back to that later on. There's some primitive notions of architectural plausibility. So, for example, one fact is that our long-distance connections in the brain, the axons are one way. It's one-way communication. So we have to respect that. And the seventh one, which I won't say too much about, but the overall plan is to explain how, in this context, we can do a few primitive operations. So one will be association. Another one could be inductive learning. And the idea is that if we can implement these basic primitives, and on top of these, it's plausible how we can do more complex acts of cognition. Okay, so basically, I do have a list of these requirements. Okay, so quickly, so why is the brain not so easy to explain computation on? Well, I think the main thing which stands out is that, as far as we know, there's no addressing mechanism. There's no address 17 you can go to. On the computer there are addresses, on the internet there are addresses, in the brain there aren't. So it's pretty hard to know how to do business in a model like that. Also, it's very slow, so the cycle time of a neuron may be 1 or 2 milliseconds, and so in 100 steps you have to do quite a lot. So neurons are sparsely connected, so each one is connected to a very small fraction of the others. So some positive things as far as modeling. So long-distance communication is something which is simple. It's stylized. It apparently happens at this electrical level by these spikes, and all the spikes look rather similar. So the main information is when they're carried. So long-distance communication is something which is easy to model. As I said, there are some serious constraints. And so I'll have 4 variables, 4 parameters. So n is the number of neurons. These are the connections to and from each. And then the synaptic strength is 1 over k. So k basically, so k equals 10 will mean that to cause a neuron to fire, you'll have 10 presynaptic neurons firing to cause a postsynaptic neuron to fire. So the issue is that if k is very large, synapses are very weak. You live in this very democratic soup where to get anything done, 100 people can have to agree to get something done. Whereas if k is small, like 1, it's more Boolean. It's more like a digital computer. So small k is certainly much closer to what we think of as computation, and large k, where with small k, one neuron can tell one other neuron to fire. With large k, you have to get large numbers together to make anything happen. So with large k, it's a very thin soup where it's really hard to find out how computation can happen. Okay, so this is so there are some facts. Okay, so one more thing. So I do have a model, but the model will have parameters because some things about the brain we don't know, and probably different parts of the brain are different. So there's no way of legislating. And the most important thing is the synaptic strength. So how big an effect does a neuron have on another? And so as I said, so k equals 1 are very strong neurons, very strong synapses. K equals 10 are weaker ones. Maybe 20, 30 years ago, people seemed to believe that k's were extremely weak, maybe 100th or 1,000th. And on the average, they could be very weak because otherwise maybe your brain would kind of blow up. But it's very important for computation to figure out what the distribution is. Okay, so if there are some very strong ones, that's important to know. And probably this varies among different species and different parts of your brain. So that's a parameter. Okay, so, okay. A couple of comments. So certainly it's, neuroscientists tell us that in fact there are many neuron types, and even many synapse types. So it's not just a question of saying a neuroscientist will find out what the real typical neuron is, and then we'll have a model of that, because there's a great variety of of them. And in fact, my interpretation is that there's a good reason for it, because the different neurons are different. They run different algorithms. So the neurons will be little distributed algorithms, and we need several different types. And what you find are different biochemical implementations of these algorithms. Okay, so so it's naive to say that someone will tell us exactly what the hardware is, and then we'll have a model of that, because the hardware is just too varied. Okay, and then maybe this is the main sentence which suggests why it's not too aggressive to try to have a model, as long as you make your model to do with tasks which are very communication challenged. Actually, same with parallel computers. The real bottleneck is always in the communication. So each neuron is connected to a small fraction of the others. We do have these long connections which go across your brain, but they're fairly slow. And as long as we analyze tasks which use communication a lot, we can exploit the difficulty in communication to get some insight. And in particular, so if you have a network which is very weak, even if you put a supercomputer at the nodes, it won't help very much. Okay, so the details of the neurons won't be so important because the communication network is so weak. So that's kind of an intuitive assumption. Okay, so as I said, I'm trying to say something useful from the computational point of view. in an area where viable theories are few. So what's the methodology? I don't want to spend too much time on this, but basically it's the following. If you cross-examine me afterwards, I'll come back to this. So basically I have a very simple model which I want to underestimate what the brain does. Okay, so I want a model which is too weak. I don't want you to tell me that the brain cannot do this. If you tell me that the brain is much more complicated, that's fine with me. Okay, it is far more complicated. I want a weak model. But then I want to list some set of tasks which I think are challenging to implement, and I don't know what other theories there are for doing it. So then I'll show that the simple model can in fact do these impressive set of tasks. Whether they impress you or not, who knows, but okay. And in particular, if one can show that this simple model can support thousands of these tasks, like we can do thousands of these cognitive tasks in a lifetime, then it's some evidence that there's some way of doing these tasks given this computational model. Okay, so I'm not modeling the brain in the conventional sense where you try to capture all aspects of some physical device, underestimating it, but hopefully in my underestimate I'm capturing the important constraints. Okay, so I'm still interested in this. Okay, so as I said, I want to describe some tasks which I think are primitives for the brain. Okay, and so I'll just describe two, and you have to start somewhere. So there has to be some task which allocates a new concept. Okay, if you learn about this green Fox restaurant, what do you do? Okay, so I have a definition of what you do. Then we can discuss it. So so first I'm heard of Donald Trump. So the only reason for using this concept is that everyone knows of this concept. Okay, so the idea is that I'm assuming chunking. So previously you've probably heard of the name Donald and the word Trump, and somehow you allocate concept for this new concept. And so the definition is that you've already got stored items A and B. So A and B will be Donald and Trump. You already understand those two, a bit like green and fox. And in this definition, I'll allocate new neuron C for this new concept, Donald Trump. And I'll change some synaptic weights so that in the future, when Donald and Trump are active, I will activate this compound concept. Okay? So the setting is that you're born with your brain. It will be kind of a random network of connections, so that's unchanged. But you can change synaptic weights. And when you hear this new concept, you will change a few of the synaptic weights. And in particular, in this state, you've already allocated some neurons to Donald and Trump. And since this is the new concept you have to memorize, you're going to change some weights near or connected to the neurons which are related to what you're trying to store. And you're going to increase some weights. You have to decide where you're going to store this new concept. And then between these neurons and this neuron, you have to change some weights. Okay? So that's a definition. Okay? What else? So I'm, of course, this is a realization of chunking, that I'm allocating storage as a combination of its constituents. And I'll say it constructs or modifies a circuit in response to the stimulus, so that the circuit will do something different. So in general, this definition is a definition. I suppose the main assumption here is that I do have this discrete assumption that for a concept like a Donald, I have a set of neurons. So is this strange assumption? Well, in some sense, there's a lot of evidence that this isn't absurd. So these are well-known experiments done, say, 15 years ago now. So these are on humans with electrodes in a part of their brain, the hippocampus. And what's going on here is that there's this patient with electrodes in their brain, and this particular, say, one electrode, and this patient is shown a picture on a laptop, and there's a recording from that particular neuron for a second. And I think these vertical lines are the second. And then this particular neuron, to this input, responds rather vigorously while the patient is shown this neuron. Okay, and then it turns out that this neuron is rather responsive to pictures which correspond to Bill Clinton, but not to other presidents or to other concepts, unrelated concepts. Okay, so there's some evidence that if you decide on some concept, so Jennifer Aniston was also another famous concept used, and you're looking for a neuron which responds particularly to Jennifer Aniston and not to other things, then you can find these in this part of the brain, and you can kind of so you show lots of pictures. Okay, so the way it's done that the electrodes are kind of fixed. In the morning, maybe you show the patient lots of pictures of which interest you, different concepts, and if you think, oh yes, this neuron seems to be responding to Bill Clinton, then you collect together lots more pictures, maybe 50 of Bill Clinton and 50 of not Bill Clinton. So you could really try to verify whether this neuron is reacting to what we think is as Bill Clinton. So anyway, so there's evidence for kind of discreteness, but of course these results have to be treated with a lot of caution because I mean, no one says that these neurons are where you're storing Bill Clinton. So if you poke around in a computer and you see some changes, it's probably information, traveling through rather than being stored there. So how to interpret this exactly, no one knows, but it's a notion of a discrete representation is not absurd and okay. Anyway, okay. So what I described first was how you allocate to a new concept. But one important aspect here in this work is, as I said, the seventh requirement is that I want to do more than one task. And so the second task is to do with relationships between what you've already stored. Besides just storing stuff, your brain isn't just a telephone book. You have to store more stuff. So this is an idealization of an association. So if you know what Donald Trump is and you know what elected president means, then at some point you heard that he was elected president. And this is what I call an association. And this is, again, this is a definition. And the definition says that you've got now two stored items, A and B, A, B. And the result of doing this, of storing this association is that you change some synaptic weights so that in the future, whenever A is active, you'll be reminded of B. Okay, so again, this is a specification of how you want your network of neurons to change. Okay, so association is a term used in many different senses in theory of neuroscience, and this is one. It's very close to how Wilshire used this. Okay. Okay, so that's another definition. Okay, so I've got some tasks here. Okay, so I do have a model of computation. I'm a computer scientist. I need to say what my model of computation is. It's an abstraction of what I think the brain is doing. So it's like the classical McCullough-Pitts model, which was formulated in 1943, but it's just made more programmable. You want a model which you can imagine you can write little programs for. So for example, timing. So the brain clearly does timing in a very clever way. So you have to program it with some timing mechanisms. And it's more quantitative. Okay, so Okay, so again, briefly, so one can give a more formal model, but the main features are that main features, in fact, are these numbers. I've got n neurons, deconnections from each neuron, and some bound on the synaptic strengths. So each neuron runs its own little distributed algorithm. So each neuron just sits there as an algorithm is ready to go, depending on what inputs it gets. So there's some constraints on what the updates can be. But basically, it's a local computation on what the on the information available to the neuron through its inputs. But basically, it can only integrate the inputs from all the neurons by some additive process. It's like a threshold. You can work on a threshold. Okay. So there's a little distributed algorithm which runs this thing. It's got some states and a few other things which are needed to make it programmable. So state, for example, means a neuron knows whether it's stored something already or not. That's a state. Also, you need states for some local dynamics, some short-term dynamics. So we need state. And there's a weak timing mechanism. So the most onerous constraint would be that the brain is kind of timed like a computer with a clock. So that's a bit onerous. So we do a very weak version of that. So very basically, maybe you cast your gaze to a new place, you get some inputs, and so your neurons start running. And so the idea is that each neuron can count, 1, 2, 3. And when it's got to 3, the other neurons have got to 3 as well. So they can keep pace for a short time. It's a minimal timing mechanism. Anyway, one can formalize all this. Okay. Oh yes. Okay. So a few other things. So my fourth parameter, I emphasize parameters, is this R, and the idea is that if I store an item like Bill Clinton, I'm going to use R neurons for it. As I said, whether R should be 10 or 10 million, no one knows. But just one comment is that when you can experimentally identify neurons which do Bill Clinton, then R must be pretty large, because otherwise you'd have no chance. If you just 10 neurons, you've got no chance. And so, for example, in these experiments, which I mentioned, the R is roughly 1,000th of the neurons. So, if you're looking for a Bill Clinton cell, and you poke into one neuron in that part of the brain, you got a 1 in 1,000 chance of finding it, which is pretty high. Okay, but it's okay. And some other parts of the brain R may be very low, and we don't know. If people poke around in that part, they can't find out what it corresponds to in the real world. So again, R is this fourth parameter, but in different parts of the brain, different species, it may all be different. Okay. So oh yes, other comment is that so if 1,000th of your neurons do Bill Clinton, does it mean you can only memorize 1,000 different concepts? The answer, of course, is no, because your sets of neurons may be overlapping for different concepts. And in fact, for this part of the brain, that's what it is. So there are neurons which respond both to Bill Clinton and to the Eiffel Tower. Okay, so there's a big clouds of neurons which may overlap. But another regime would be that they're disjoint. Maybe you've got 50 neurons for each concept, and they don't overlap. Okay, so when they overlap, it makes computation more difficult because there's more chance for confusion, for errors. Okay, so then in fact I've almost told you everything which you need to know, and the rest you can deduce from what I've said, almost. So we just have to work through the implications. So what I said was that you're born with a big random network, and somehow you go through life, and the world throws to you some challenges. So it says, you eventually somehow memorize who Donald Trump was, and then somehow you memorize what elected president means. But then this act is actually memorizing this association that he was elected president. So how would you implement this this task? And so, as I defined a few slides ago, what I want to do, I want to change some weights, so that in the future, when these neurons fire, these neurons will fire also. Okay, so that's all I said. And kind of constraints on this I've kind of told you already. So this will be a big random graph. You have n neurons, maybe 10 to the 10. There's a probability of connection between each pair. Okay, and R is how many neurons you use for each concept, and K is this inverse synaptic strength. So what's meant is that, so this may be a million neurons, this may be a billion neurons. Each neuron is connected to a very small fraction of the others. But say if K is 20, you need 20 neurons to cause a neuron to fire, then really of these million neurons, you only need 20 of these million to be connected to this node. Okay, so the picture is you've got a sparse network, but there's a minimal interconnectivity requirement. Okay, so is that clear? So I've got these 4 parameters, and they're interrelated. Okay, so if I give you 3, you can deduce what the 4th must be. Okay, so just saying it again. So probably a typical regime would be that, you've got a million neurons for each concept, and when these fire, you want these to fire. To cause one of these to fire, you need at least, say, 20 of its presynaptic neurons to be firing. So certainly you want at least 20 of these million neurons. You want at least 20 to have connections to this one. Okay, so this is the game quantitatively. So this becomes some random graph theory, and one uses that's the binomial distribution. So for neuroscientists are very familiar with the Hebb rule, which is about you've got two neurons, and if you stimulate them together, then Hebb's rule says that you're going to increase the strength of the connection, if there is one. So in some sense, my association is like a systems level Hebb's rule. I'm saying, instead of looking at single neurons, like Hebb did in 1949, it's time we looked at big sets of neurons, and to say that what their effect is through the network. So in some sense, what I'm talking about is not exotic at all. Okay. So hierarchical memorization is the other task I discussed. It's a different task, but it's very similar, similar requirements. Okay. So actually, the problem formulation is just slightly more complex, because when you fire the Donald Trump neurons, you do want to fire the president neurons, but you don't want to fire too many other things. So far I've discussed the positive effect you want to have, but you want to evade extra noise or side effects. Okay, and to do that, what you finish up with is a more complex semantics. So in particular, when you say these million neurons represent Bill Clinton, what do you mean? Okay, so roughly these numbers are just dreamt up, but roughly I mean that when at least 95% of these million neurons are firing, yes, you're thinking of Bill Clinton. When less than 30% are, you're not thinking of Bill Clinton. What about in between? Well, I make sure that never happens. Okay, so because of statistical phenomena, this thing acts slightly more Booleanly than you'd expect. Okay, so just because of the force of large numbers, you simulate some more deterministic phenomena, and the random graph theory shows you that. Okay, so you need some semantics like this. Okay, so with this kind of model, you can do computer simulations, you can do mathematical analysis, and as I say at the end, you can biologically test whether the brain can do this. So I'll say something about each. So this was a simulation done with Vitaly Feldman. So we had so associations, exactly as I've described, hierarchical memorization, and 2 other tasks. And we just threw these tasks at this network and asked when does it fill up? Okay, there's a capacity. After a certain amount of time, it just fills up, it makes mistakes. Okay, so again, the point is that by doing a task, a task is really something which, by doing a task, you acquire a responsibility forever later. Okay, so if you memorize an association, you have to be able to do it forever later. Okay, it's not just, you haven't finished with it. Okay, so when you hear of Donald Trump, after whatever else you've learned, you'll know that he was elected president. Okay, and then then we tried various numbers. Okay, so we tried to find out what the capacity is. we piled on these things, and eventually the thing failed. At what point did it fail? So we tried different numbers to get something impressive. Well, the details depend very much on the details of what we tried, but this was our first kind of experiment. So this is like 10 to the 8. It's like 10 mouse brains, a fraction of our brain. 8,000 connections per neuron. That's kind of typical, say, for a mouse. So the synaptic strength, that's what I say, no one can tell us what the right number is because it varies in different parts of the brain. So, okay. And then with these, we figured out that the number of neurons to represent a concept was like 360,000. So this is like a 300th of the total number of neurons. It's roughly in the ballpark of these Bill Clinton experiments. And then we could support this many operations, a few thousand operations. Okay. So how could we do better? This is a disappointing number. So if we went to stronger synapses and a slightly different scheme, then we did go up to the number of actions which are more like what we're interested in, like what humans can do. And again, without otherwise realistic parameters. Okay, so in many ways, if you do a random graph model, then a simulation is a pretty good way to go. You can get kind of pretty good estimates of what's going on, and analysis may be impossible to do in a complicated situation. So that's a possible thing to go. Okay. Okay, so for any converters into slightly more neuroscience language, we decided that there are kind of two regimes where things looked fairly good. So one was with these weaker synapses, other one was with very strong synapses. So with weak synapses, we had very large R, like the Bill Clinton thing, but we had to use shared representations. And so the hippocampus is where these Bill Clinton cells are found, and so that may be a good representation there. Capacities were moderate, but these algorithms are very simple. So probably, basically a random jumble of neurons kind of does this. So the idea that this kind of so random jumble of neurons did something useful almost at the beginning is, in this sense, is kind of plausible. So with strong synapses, slightly more complicated algorithm, I'll get to it. You've got good capacities. Need few nodes to represent a concept, so it's harder to verify experimentally. Okay. So anyway, so this is just converting what I said before. So this is analyzing this. Okay, so it's just slightly more detailed. There's the two regimes. The first regime is what I showed you. The one which gets a distinctly higher capacity is where you have an intermediate layer of nodes, and these have very high synaptic weights. Okay, so here you got the same degrees, same numbers, but a single neuron is enough to cause this one to fire, which in effect it blows up the effective degree of these nodes, but it makes mistakes much more likely to be made because it loses independence. Okay, so these are the better ones. Now we could also analyze these. Okay, so I won't give too many details, but if you want to analyze this, so the task association, it says, I want Donald Trump to be associated with elected president, and I give a long list of other associations I want you to do. And what the random graph has to do is that if you fire all of the nodes of Donald Trump, you want to fire all the nodes of elected president, but you don't want to fire any of the other nodes. So this is some extreme version of association. And you ask, can these random graphs support it? And so you can prove theorems that asymptotically you can do pretty good things, and I won't give you the details. And the second scheme, where you have got these intermediate nodes with the high synapses, do give you high capacities, so you can justify it. Okay, so going back to neuroscience, so you can ask, well, do we know the actual values of these parameters for any living organism? So they are pretty hard to find out. Even the, I suppose, number of neurons you can estimate, degrees, kind of, but even those are vague. So synaptic strengths, so in the olfactory system of the locust, in the olfactory system of locust, there are studies which give you all 4 parameters. So the R here means that if you give the locust a natural odor, how many neurons are active. Okay, so in some very few systems you can figure out how this random graph theory corresponds to what goes on in biology. Okay. But what I want to finish on is the idea that these kind of theories, one can test whether, say, the brain of a mammal can do these tasks. What it actually does is something else, but is it capable of it? So the idea is that so in-circuit testing, I think that's some old-fashioned word from electrical engineering. So the idea is that you've got some circuit board, you can certainly test input-output, what it's doing, but if you really want to find a fault in the middle, you put probes very near the, around the components and see, put input-output for the local components and see what that does. So, okay, so with this idea, one should do certain experiments on the brain. You see, because what I'm saying with associations is very simple. So the hypothesis is that if I've got a random set of nodes, say representing Donald Trump, another random set of nodes representing elected president, so the theory is that if I somehow stimulate these 2 sets according to some protocol, then the end result will be that later on, if I just stimulate these will become active. Okay? And so the question is whether this network which the brain has is able to do this. Okay, so I've got some algorithms which are able to do this. Is the brain able to do this? Okay, and so in principle, these kind of experiments are on the point of being doable. So actually, as far as methodology, so neuroscientists actually don't like these in-circuit experiments. They want natural inputs and natural outputs. Okay, they think there's something artificial here. But okay, but I really want to find out what are the basic building blocks of computation in Cortex, how Cortex actually computes. So I don't want natural inputs and natural outputs because who knows what side effects that causes in your brain, which you can't explain. You want to keep things as simple as possible. So you just want to stimulate these neurons. But technically, the difficulty is that you're going to train by stimulating both sets, and then you're going to test by training on this and recording from this. So there's a challenge in both being able to stimulate and record from the same set of neurons. You want to make sure it's the same set of neurons. Okay, so that's kind of it's on the electrically, optically, it's kind of doable now. I think if you try hard enough. But I mean, there are questions like we've got no idea. If you take a piece of, if you take say a monkey brain, we've got no idea how big R is. This is how I started. Is it R 10 or is it 10 million? And the experiment will probably work if you've guessed the R right. Okay, so there's no reason why the part of the brain which does associations should be able to do this, I think. But other parts of the brain, there's no reason why they should. And if you don't use the right R, there's no reason why it should. Okay, so I'm not saying this is trivial to find out. Okay, so there's some hope of doing this. So again, more on the experimental side. So my impression of in experimental neuroscience, there's often a lot of kind of overtraining. So often, when you do behavioral experiments on monkeys, you train them for 3 months to do something. which isn't so natural. And also with electrical stimulation, you put in very intense currents and see what happens. So what I'm pointing to is that maybe you can do much more natural experiments. So if I say blue monkey, you can memorize that. So in a fraction of a second, you can change your brain to do something. So that may be because there are effects which happen when lots of neurons are active and there are small changes in synaptic weights. Okay, so I'm discussing this large statistical phenomena where each change may be small. And if you're looking at each change, if you're looking at a big small change, you probably have to train for a long time, but that's not what I'm looking at. Okay, so there may be new phenomena here to find. And so there are some experiments. So there are some people who do experiments reminiscent of this kind of thing, but not exactly what I'm saying. Okay, so lastly, there are other avenues from which one can hope to get experimental results from neuroscience, which would help to converge on a theory like this. So connectomics, which I gather is done here in a big way. So here you want to find out maybe facts about how neurons are connected, statistical facts, actual connectivity. Okay, so optical stimulation and recording. So this is what I've been discussing. And another, a third direction, which is very promising, is various kinds of imaging. So this MEG is a way of doing imaging in the brain, which has very good time resolution. There's not so good space resolution, but as far as the timing of these various mechanisms, which one hypothesizes, there's reason to believe that maybe those are accessible also with current technologies. Okay, so the conclusion is that the kind of theory I'm describing was kind of pie in the sky maybe 10 years ago, but now there's much more hope that testing a theory like this and converging to the right theory is within reach in the not too distant future. Okay, so thank you.